It will be, I hope, not too tough, but it's quite technical. There is not much picture or nice things to look at, but we try to enter in something like demystify the famous psychrometric chart, no? I think this is...
First you can ask how many people know about psychrometric chart.
Yeah, okay. So who is able to use it?
First of all, how many know about psychrometric chart?
How many know? Okay. And who use it? Who has used it often? Okay. Be proud. And then the one who have done it in exercises in school or in college. Okay. Okay, so about half. Okay, so it's a famous because it's always something that when you don't know it, you think it's a little bit a mystery. So the goal of this session is to try to give you an understanding of the construction of the psychrometric diagram and somehow be able to use it, because you will see it's not so difficult. And so we'll try to cover simple things in the psychrometric, sensible heating, sensible cooling, a little bit dehumidification and evap. That's the four processes I think we will go through really. And we will try to make few exercises together. And then relate it also to air handling unit in a sense that at some point it's interesting to relate it. So, and then at the end we hope that you can at least read also. It's not only use it yourself, but get it explained by somebody. For instance, if you are an architect, you ask the engineer to explain. It's I think it's a good tool for that. So what we will try first is to explain how you construct this, because the best thing to understand a kind of abacus or diagram is to understand how it is built.
Here, do you want to be separate one copy?
Oh yeah, we can.
So that if people have to refer to it?
Yeah. I think the idea is to give three for each, but we can. So why do we have to take care about temperature, humidity? Of course, it's thermal comfort and energy related, because actually it's not just thermal comfort, but it's how you maintain it or how you derive from it. And many of these principles can be drawn on a psychrometric chart, and they are also quite logical when you show them on this chart. So that means it's not so difficult to follow something on the concept level. And I think it's still, I can say in my opinion, it's still maybe the fastest tool or method to understand. When I say fastest tool, now it can be also on computer. Often it is on computer, but still knowing how to use it on paper lets you use also on computer. And I think you can get explained or explain the HVAC strategies or even natural ventilation or different things with that. So this looks like an old story, and it was definitely, I think maybe you have not lived this time where there was no pocket calculator. There was only the log table and the slide rule. So you can say a long time ago people were looking for a kind of abacus which could help in doing some calculation. The advantage of this, I would say, is not only that it's not digital, it's analogic, so it's easier to visualize things. When you crunch numbers, you get numbers, but how do you relate? No, 22, 55, you don't visualize. When you see a difference graphically, it's a big advantage. And the ASHRAE did a kind of celebration of this 100th anniversary of this diagram, which is typical ASHRAE kind of thing. And they were saying that something like 70% of the HVAC engineer was still using the diagram in the 90s. So, so now you can say it's as I mentioned, this is taken from the Ashbury Journal at this time, and they were saying also that before 1960, especially, there were nothing like computers, and you can say in 1995 still 3/4 of the practitioners were using. Now, of course, the printed psychometric chart will slowly disappear, even though I think you can still buy the sheets in some shops. And you can say nowadays the psychometric software are used, but actually they use the method of the psychometric chart. So some of them are more sophisticated. You can enter a number of things into it directly. But the principle remains the same. So if you have understood the diagram on paper, you will understand very quickly or directly understand what happened with the software. And the interesting thing is you are doing some calculation, some graphical description at the same time. It is certainly, it's an easier process. And also, I think what is important, it's an entry in the dark world of HVAC for architects. I think it's something which is also helpful. And because if you look at HVAC, I mean, if you get as an architect or even as an engineer, if you're not a specialist, if you get this kind of very nice description of what the guy will show you and say, there, this is this HU we have and this and that, you don't make any sense out of it. Whereas the psychometric diagram, we'll see it later, it's something which helps you in getting an understanding of that. So now the first thing is, everybody knows what is wet bulb? Raise the hand. Wet bulb temperature. So raise higher, I want to count. 1, 2, 3. So not half even, huh? So I think we have to explain a little bit what is the wet bulb then. The wet bulb is, let's say today, for instance, if we look, I just looked before, I have a sensor. We have a temperature of about 24 degrees now and about 35, 38% relative humidity. This doesn't tell much. I mean, it tells that, okay, we are in the range of comfort, fine. But then if you would like to cool, of course, we are not in this situation, but suppose we would be at 40 degrees and 20 or 15% humidity, that's what you would know by a sensor. But at the time there was no sensor, there was no way to measure relative humidity apart from very specific device. And then that's how the wet bulb came, you can say. The wet bulb is simply that you have a sensor. One is dry and the other is contained in a kind of wet. We call it wet bulb because it is actually, this is something like that. So you have a fan which is drawing the air through these two channels. This one is dry. If you take that an old system which is no more used today much, but still very accurate, and then you put something like cotton wool and you completely moist around the bulb. And if you draw air through the two, then you get the difference of temperature. This one is called the wet bulb. That means this is the temperature of air which would be saturated at 100% of humidity, maximum relative humidity. So,
Is it clear to people who do not know about the wet bulb, that what is happening here?
we will explain a little bit more. So here, this is a typical thing that is used often in India and is used in many places in the world. This is called the sling thermometer. What is it? Is that you have a handle, a chain, and then you rotate the two thermometers here. This one is dry, and this one had this wet bulb. That means you have this moisture. It's completely moist, and by going fast enough, you are getting speed, really making that the temperature here represent 100% relative humidity in the air. And that makes that you get these two difference, which is the difference between the dry bulb and the wet bulb. So now I'll show you just an example that I have prepared. at home actually in Switzerland, so it does not relate to the Indian climates, but it's still the same. So now if you look, we had a kind of classical thermometer and a so-called modern sensor, electronic sensor, and the two were giving about approximately the same dry bulb temperature. Then after, what we did was to, so this is then the measurement that corresponds here, and you have this here. And then we have the dry bulb, and then we try to measure the wet bulb. So how did we do it? We just take some piece of cotton wool and then make it moist, and then had the fan which is sucking the air, and by putting this bulb, wet bulb, on something where the air was going through, then we are getting this temperature. So it's something which gives you, so by drawing air in both, we get these two temperature with two similar, exactly the same kind of thermometer, but this one is dry, this one has a wet bulb. And then there is an expression which is used for this, which is less common now, but was used by people. It's called the wet bulb depression. It's not an areas breakdown. It is the difference between the dry bulb and the wet bulb. That means the difference between these two thermometers. And here with the sensor, we have the temperature and the relative humidity. So now how do we link these two? So we can, there is a kind of humidity table which corresponds to this. That means here you take the dry bulb and enter it here, and then you take the wet bulb and enter it here. So 6.8, approximately 7, and then almost 22. And that gives you 46%. You see that this matching actually quite well. So this explained a little bit how today with a sensor which is measuring temperature and RH, you can also compare it well with what you do with the, let's say, the so-called psychrometric. So does everybody understand this? So typically in places like Ahmedabad or in Jaipur, in summer you may have 40 degrees outside and get a wet bulb. The dry bulb might be 40 and the wet bulb can be as low as 20 sometimes. So which makes 20-degree difference between the dry bulb and wet bulb. We'll come to that later when we talk about evaporative cooling. So, why? Why is it lower? That's a good question. Is lower because when you have dry air, then when water gets evaporated, what happened is that the water to evaporate needs some heat. And this heat, normally it happens in, let's say, an enclosed or somewhere where there is no other energy coming. So it's the mixture between the air and water which is evaporating. The moment you evaporate water in air, the air is cooled. And that's basically the evap cooling. We'll come to that after. So just as a reminder, it is based first on the ideal gas law. I think you know all about this. I will not talk much about it. Then what is important to understand for this diagram is what is the Dalton's law, which is the partial pressure law. So the partial pressure law, who knows about Dalton's law? Can you raise hand? So it's important maybe to explain this, which is, I think it's important because if you understand that, you understand how this diagram can be constructed. So actually what happens with air is that the molecules of gas at low pressure, at atmospheric pressure, they don't see each other in a sense. You know, it's like people in the metro, they don't talk to each other in the queue, no, or in the corridor. So they can be black, white, any color, they will not mix. So the air here, when it's dry, would be equivalent to the total pressure, the dry air partial pressure. But the moment you add some vapor into the air, the vapor will see its own pressure as if there was no air. That means if you imagine you have a container, if you put some air and then you add some vapor, it will increase this, but each one would keep its own vapor. It's very difficult. You cannot measure directly the partial pressure. You can just calculate, and or you can do it by sophisticated means. But remember that you can sum up the partial pressure to get the total pressure, and the total pressure in the atmosphere remains constant locally. You can say, so the moment you add water vapor, the partial air pressure will reduce, but the total pressure of the two will be the same. And mostly you have, so the other thing which is important is that this vapor can mix with air without knowing each other, in a sense. They don't talk to each other. But at some point, when the vapor becomes too dense in the air, then it starts condensing. That means it will start condense. And that's where you have what is called the saturation of the vapor, water vapor in air. So typically there are some expression which have been calculated. It has been measured first, but then some expression show that, for instance, if you have 5 grams of air at 25 degrees, you could calculate and measure that you have about 20 grams. If you add 20 grams of water, no, 5 grams, sorry. 5 grams of water, it would give approximately 25%. We'll come to that more in detail after. And then the maximum, the saturation is about 20 grams of air at 25 degrees. That gives you a little bit the idea of maximum absolute humidity. So absolute and relative humidity, it's important to understand. We'll come to that later in the diagram. So now if we come to the saturation pressure of vapor, so if you plot it, you can see that at a temperature between 0 and 30, you have a water pressure between 600 and 4,000 Pascal. Compare it to the pressure of ambient, which is 100,000 approximately. The atmospheric pressure is 100,000 Pascal. Pascal is a Newton per square meter for the one who would have forgotten. But basically it's the atmospheric pressure is 100,000 Pascal, and the vapor pressure, you see, it's only in the range of 600 to 4,000 it can go a little bit higher. And then the other thing to understand, so this curve, which is the saturation, is very fundamental. We will come to it after. If you have any question, you can always raise your hand and interrupt me. Yes?
So when you say that actually the water vapor saturation pressure
Yeah.
is 600 Pascal,
Right?
it means that if you add more vapor to that,
It will condense.
it will condense.
Yeah.
Or when you look at 15 degrees centigrade, and you say the saturation vapor pressure is 1700,
Yeah.
right? That means that if I lower that temperature, some vapor will be.
Yeah, for instance, you can think of meteorology, that when you have a mass of clouds, which are more or less near saturation, you can say, I mean, to get this fog, this color, then the moment they move in a cooler atmosphere at mountain level or something, then they start discharging. So that means when you are, suppose you have a cloud at 30 degrees, if suddenly they are at 0 degree, they will lose this almost 4,000 Pascal in pressure and corresponding to water which will be condensing. That means rains. So now another thing which is important to understand is the difference between the, let's say, relative humidity and vapor pressure. Actually, this saturation level that you reach with partial pressure of water vapor is 100% humidity, right? Relative humidity. Now, the pressure is proportional, you can say, at saturation. Let's say if you have typically at 20 degree, if we say 2000 this curve. This is this 2000. At 20 degree, we say saturation is at 2300 Pascal for water vapor. Now, you can see that the ratio is that if you have, let's say 70, if you want to have 70%, then you simply see how much would be the equivalent vapor pressure. So this vapor pressure will be, then gives you the relative humidity. The ratio between the vapor pressure that you actually have and the saturation vapor pressure gives you the relative humidity. So one thing which is important is who knows about absolute and relative humidity, the difference? Raise your hand, the one who are. So relative humidity is essentially what we human beings feel, and the paper as well. I mean, you can, if you are beyond 80%, you can see that all your paper are starting, let's say, moving, or I don't know how you say, it becomes a little bit, so the relative humidity is something that we feel. If it's too dry, we feel it's too dry. Below 30, 15%, we feel it's really dry. And above 70, you can say we feel also. For instance, when you land in Mumbai suddenly, after coming from Ahmedabad in summer, then you will feel suddenly that your hands are wet. So this is directly the kind of feeling of relative humidity. But in the calculation, we use a lot, generally, the absolute humidity. Because the absolute humidity is something which is the actual weight of water per kg of dry air. And this is something that you can use for some of the process you will see later in the diagram, and it's very important to understand the difference. The relative humidity is something that you feel, and it has no meaning at all because it varies with temperature, whereas the absolute humidity will be a constant as long as you don't add or remove water vapor in the air. So I think there is a relation between the absolute humidity and relative humidity, but I don't think it's useful to go there because you don't need that for that. So typically, another important physical value is the dew point. What is the dew point? The dew point is physically when you are reaching a level where there is some condensation on a surface, for instance. Suppose, for instance, when you have cars where people keep their AC at 16 degrees inside because they like it, and outside it's 32 and 90% humidity, you will see that it makes a lot of droplets on the screen, outside, not inside. In Europe, when it's cold, if you have single glazing, you will get water flowing on the vertical glazing because it's too cold, so the humidity will condense on the glazing. So the dew point is the point where you're on the saturation curve, but you just have air touching this surface and condensing locally. It doesn't mean. So we'll show this on the diagram. So essentially, you have these three important, I would say dry bulb and wet bulb, but the most important dew point is also important, but I would say we'll see it on the diagram later. So what we are going to try to do now is to construct the psychrometric diagram. That means we try to make it simple, but at the same time, that's how you can understand why it's looked like that and how you could use it. So first, we need to understand better what is the energy relation with air and vapor. And so the enthalpy is always a little bit a mysterious term, which is actually the internal energy of a gas plus the work of pressure which is related to its change in volume. So the total gives what we can call the total energy, which is called enthalpy. But you can keep it in your mind as energy. It works the same in a sense. For calculation, it will be enthalpy or energy will be same in the diagram. So the next, so now if you look at what is the enthalpy, what does it contain? one is the sensible heat of the dry air. That means we will come to that after in detailing a little bit more. And then you have the vapor which is coming when you evaporate water in the air, which has also a content which has latent heat. That means that the latent heat you have to give for making water vapor from water. And then it's also when it expands to take its space, that makes what makes the enthalpy part of the humid air. So typically you are adding the dry air and the water vapor. So now there will not be much equation, don't be afraid, but I think it's important just to try to go through how do you come to the enthalpic lines, because in the psychrometric diagram that we are going to construct, we will have lines where you have absolute humidity, you will have lines where you have temperature, and you will have lines which are of constant energy, which are across the diagram. And I think it's important to have these three basic understanding of the lines. So now if we look at what is the enthalpy of dry air, generally it is from the ideal gas law, you can say it is proportional to the capacity, Cp, the capacity of the air, multiplied by the temperature. And as a convention in the psychrometric diagram, 0 degree is 0. That means Cp into T equals 0 is 0. That means the energy of the air at 0 degree is considered as 0. If it's below 0, it will be minus. If it's above 0, it will be plus. And then what you have to add is the enthalpy of the water vapor. And again, everything is referred to 0 degree because at 0 degree, you can calculate the latent. If you have vapor at 0 degree, the latent heat that you have per kg of water to evaporate is more or less exactly 2,500 kilojoule per kg, not per degree. There is a mistake here. It's and then after the vapor, when you heat it, like the air, has also a capacity. Heat capacity, which is a Cp of 1.82. So now, if we look at how you can calculate this enthalpy being referred as H, the total enthalpy, is actually the capacity times the temperature of the air, dry air, plus the humidity ratio. That means how much portion of water vapor you have in addition to the air. And this is then the latent heat plus the temperature of the vapor. And by adding all this, you get this very simple equation. And based on that, you can, starting by, if you solve this equation for temperature and absolute humidity, then you will get some straight line. We'll see that after. So this is just to explain that there are these three main things. One is the absolute humidity, which is how much water in kg of water per kg of dry air you have. Then the second is the temperature, the dry bulb temperature. And the third is this enthalpy. These are the three main, let's say, things which will come in the diagram to make it workable. Yeah?
H stands for enthalpy.
Each?
In the equation,
Yeah.
R or H.
H is enthalpy. Yeah.
That's the sum of these three components.
Yeah, exactly. And so after that, you just solve it for temperature and the humidity. And then you get some straight lines because it's a linear, so you will see that when we build it. So now, to start with, we take a completely empty diagram where we have only two axes. So the first axis that you will see, the horizontal axis, where you have this vertical line, is the constant dry bulb temperature. That means these lines here, along here it's 30 degrees, along here it's 20, etc. So the dry bulb temperature you will see on this axis, but wherever you go it will be the same temperature along this vertical line. Then next axis is the vertical axis with the constant absolute humidity line, typically going from completely dry air to air which has a lot of water. So you see that generally we talk of 0 to 30 grams. In India, sometimes it can reach 30 grams. You can say 0.03 kg of air per kg of dry air. So 30 grams, this is the kind of maximum that you get. So this is really the basis of how this diagram is constructed. Then after we have showed you before this saturation line, that means this line represents the relative humidity at 100 degrees. So here you see that depending on the temperature of the dry bulb and the humidity ratio, you can see that, for instance, at 20 degrees, you have about 14 grams of air at saturation. And at 25 degrees, approximately 20 grams. So that means above that, you cannot go. It will condense. So where you can be with the diagram is only in this region. Here, you cannot normally go physically. So the saturation curve is at... So now we have seen that based on what we have seen before, we can draw this curve. Now what we need to do is to have this relative humidity we were discussing before. So this is the absolute. This is what you would have on the weighing scale. If you would add water or vapor, let's say in an environment, you would sum up with the dry air, and typically you would get normally, if you would weigh air completely saturated at 30 degrees, at 35 degrees, you would have 1 kg and 36 gram, the mass of air plus the mass of water, which is in vapor form. So now, remember what we showed before, that the relative humidity goes with the partial pressure. So this is the humidity ratio in absolute term is something which is proportional to the partial pressure that we discussed before. If you look at each of these points, corresponds a mass of air, but correspond also a partial pressure. So now what we have seen before is that the partial pressure, if you say, I want only 75% of the 100%, then I will just multiply all this point by 0.75. And so I get, so by doing that, I will then be able to draw, for instance, for this point, I would have this point at 75%. So then you can draw the first, let's say, I have made a very simple diagram so that you can really see the curve. The one you get is much more complex, but it is the same. It's not different. And then you can substantially, you can get, let's say I have shown only 4 relative humidity curve. I could have shown more, but I think it's, so you can really see that if you go along this line, this is 25, you can divide this by 4 and you are here. So all these curves are in relation to this one. So this is then the relative humidity. This is the feeling that you have more on when it's dry, you are here. This is, let's say, extremely dry and hot weather. And this is typically Mumbai. So now we have seen that we can place the points. If we know the relative humidity, if we know the temperature, or if we know the temperature and the absolute humidity, or if we know the relative humidity and the absolute ratio, we need only 2 to find the third, in a sense. It's always like that, huh? So if I tell you, for instance, what is the saturation, if I'm at 25 degree, how much humidity ratio I have in absolute value at 50% relative humidity? Huh? So this one we say, huh? So 14 gram, right? Approximately, huh? We are not at 3 digits, we just look at the principle. And then now the question is, okay, now we are able to place this different, we can know, depending on if we know how much absolute humidity we have or how much relative humidity we have, we can now place the points of the diagram. But we still don't know the relation with energy. So now we remember of this equation I just showed you before. So for that now, from this, we can draw the line where enthalpy at a constant value. And then we can add, this is the first one, I have shown only 3, but it's for the principle, you will have many more on the diagram. So this corresponds, if we say 0, the enthalpy of air, moist, and vapor is at 0 degree is equal to 0, then this line is 20. And so you see it's something which is a kind of diagonal, it has a slope. And then we can see that next we can add the 40 and the 60. I have not added more than that, but just that you can see that now we can start not only place the point, but we can also start, let's say, describe processes. That means we can go from this point to this point, and then we can make some relation, knowing that these curves will tell us the energy level of each of these points. So that means we could start doing some energy calculation. So this is the basic principle of the chart. There are more information on many charts. There are things like the density of the air, but in the range we work, the density of air between, let's say, 20 and 45 or 15 and 45, it doesn't change so much, so we can more or less neglect that most of the time, the variation. And then, so this is in a sense a complete, simplified cycle. So now I will show you the simple processes that you don't make exercise now, but I show you just the principle. So now if we go still on this simple diagram, so if we say we want to heat air at 20 degree and 50% humidity, yeah? So we are here. It gives approximately 7.5 gram if you can see. That's what we can read from the chart. Huh? And then now if we say from this point we are going to heat up to 30 degree and 75. You see that here what is important to realize, the relative humidity is going to change even though we are only heating. We are not adding or removing vapor. The water vapor remain constant in absolute value. So the interesting thing is when you do sensible heating, you see that we are along these lines. That means we don't change the absolute humidity. That means if you are heating a mass of air, it will move along this constant humidity ratio. And then if you heat up to 30 degree, then we can see how it is. So here I don't see the energy, I will do it at a later stage. This is now to show the cooling now is exactly the same process, reverse. Simply you start from, let's say, 30 degree, 25, and you want to cool it to constant humidity. That means only sensible, there is no condensation. You are not cooling with a very, very cold cooling coil. And then you are cooling the air to 20, and you come back to this 50% of humidity. So you see that when you cool the air, the relative humidity is going up. When you heat the air, the relative humidity goes down. So this is something you should keep in mind, that it goes always in this direction. And you see that this sensible heating and cooling are on horizontal lines. So this you can remember because it's very simple in a sense. Then one other process which is very interesting is evaporative cooling. So evaporative cooling is the desert cooler or passive downdraft evaporative cooling, or all kinds of systems which use evaporative process to cool the air. So now we start, let's say, in typical example at 35 degree and 25% RH, relative humidity. So which means we have about 9.5 gram per kg of vapor per kg of dry air. Then now we are going to, we fully add vapor, that means we spray water in the air. So what will happen? If you spray water in the air, it will evaporate if it's fine mist, and then it will cool the air. But then the humidity in absolute term and relative will increase. So that means we are going to get what we call the iso-enthalpy curve. What is it exactly? Is that the thing which is interesting with evaporative cooling is that if we have no heat transfer from outside, that means if you only spray water in the air and there is no other thing that are heating or cooling, there is no heating or cooling coil or any surface, then this is what we call an adiabatic evaporative cooling. That means you have, and so it stays on the same energy lines. That means you are not heating, not cooling, just spraying water, and you are getting the air to be cooled, but relative humidity and absolute humidity increases. So by going from 25% humidity and 35 degree and spraying water and going up to increasing from 9.5 gram to 14 grams of water in a kg of dry air, you are going to reach something like 70-75% relative humidity or 14 grams, and you will have decreased the temperature of the airstream from 35 down to something like 23 degree. You follow this as so it is. So remember there are these horizontal lines for sensible heating and cooling. So just I show you again so sensible cooling is if you have a kind of cooling coil, but which would be with water maybe at 16 degree, not at 6 degree, then you would cool without condensing the water. And then when you go for evap cooling, you have to follow this enthalpy lines. You can see them on your diagram. You can see on the top of the curve. I'll show you after because we have the same diagram after. Yeah. Yeah.
Then you are basically taking away heat.
Heat, yeah, but no water.
No water.
Yeah.
Not changing the water content, but
No.
you're changing the heat content.
Yeah.
Removing heat.
Right.
So then you have to, because water is not changing, so you have to be on the same humidity ratio line.
Yeah, exactly.
And now when you switch over to evaporation cooling, you're not changing the heat, but you're changing the water content.
You are not changing the total heat. That means the heat of the air goes down and the heat of the vapor goes up. It's a kind of balance. It's adiabatic. That means there is no exchange of heat with outside, let's say, this volume of air and water.
And the law tells us that in such a condition, it will always follow the enthalpy line.
Exactly. So now something which is we enter more in the, you can say, in the HVAC now, in a sense. We try to see when you're cooling with dehumidification, because typically when you start from air at let's say 35 degree 25 RH is not so much water, if you think only 10 grams, but nevertheless if you want to reduce, when you are going this way alone, your humidity goes up, and we know that let's say conventional here, these numbers, I'm not telling all these numbers are the right one. I'm showing you example on how it works. We can discuss after the real numbers that we need. And there, what is happening is then we are now going from, we are cooling sensible up to, let's say, the saturation. In reality, if you are going into a very cool coil, it will follow a line, not a straight line, but that's just to get, normally we always show this like this, that up to the saturation level. That means we are cooling the air from 35 to approximately, how much is it? 13 degree. And then we want to cool it further because we need to dehumidify, because the HVAC engineer told us he wants to keep a lower level at relative humidity. This is the one that's more important for comfort. Then we are going to dehumidify, which means we are going to cool, but we are going to condense. That means the cooling coil in the handling unit will start dropping water, and the water will have to be removed. And so this is typically the kind of thing which happens, let's say, in a cooling coil in an air handling unit, where you have water maybe at 6 degree, or so, where you are cooling first sensible only, and then you are cooling when dehumidifying, you are removing a lot of latent heat. So you can see that this energy lines, we are crossing them in a sense, right? It goes from this one, and we are going down almost to this one. And then we will come more in detail to how it relates between dry and air and latent cooling. So now I just touch a little bit of comfort, because it's not the goal of this, but just a little bit to explain that the comfort, that the sense of comfort that you get in a psychrometric chart is still air, you can say. There is no air movement. It is, let's say, based on historically on the ASHRAE standards of the late 50s maybe. So you don't consider that air is moving, you don't consider there might be a ceiling fan, you don't consider that there is maybe radiant cooling, or all these things. So this is not taken directly into account. But then when we start looking at how you can somewhat take into account for the comfort assessment, is that these are the typical, let's say, very conventional comfort zone. That's the relation, let's say, between the processes on air in the diagram and comfort. We can define more or less, generally the ASHRAE old comfort zone say that between 20 and 30, but this is even already enlarged, and up to 70, 80%. You have, let's say, an ASHRAE comfort zone, so to say. But then if you have fans, actually you are better off. So depending on the velocity of the fan that you have around your head, you can increase, in a sense, this comfort zone. So I don't go much in detail, because tomorrow I know that Rajan will talk about that. So it was just to show you that the comfort zones are also addressed traditionally. For instance, Givoni, one of the famous bioclimatic scientists, has developed this kind of region, which have been taken later by climate consultant. Does anybody know climate consultants, the software? Raise your hand. Okay, so actually climate consultant is using the kind of assumption that are used by Givoni, which were designed many years ago. But it's a kind of way of looking at different strategies, so that you can, in a sense, broaden the zone of comfort that you can see. So it can help you in looking at processes and see where you are. Another thing that you should know, and I think Rajan will talk about it tomorrow, is that there is a new Indian model for adaptive thermal comfort. So here I don't go, I just mentioned that because this can be also somewhat coupled sometime with the psychrometric diagram. So now we are going to make some example and exercise together. So just remember now, sensible heating in the diagram is like this. That means you are going from left to right, you increase the temperature, but you stay constant on the absolute humidity. Sensible cooling, you are cooling like that, and if you go up to the end, you are reaching the saturation curve. That means you are going to reach the dew point, what is called. That means for air at a given air absolute humidity, if you cool sensibly up to the saturation level, it will start, you are reaching the dew point. So if you have a surface which is at below this temperature, it will automatically starting dropping on this surface. Then after you have cooling and dehumidification. We have seen before it goes this direction and this direction, so it goes in the left and also down, you can say. And then evaporative cooling is, on the contrary, going up along the enthalpy lines. So this is a little bit so. Has anybody question at this level on how is the diagram constructed and how it looks like? You think you could start using it? So we'll see. So here we have just a reminder for your basic physics, how you can calculate energy and power to be used on the psychrometric. So we have seen now that we have these enthalpy lines, which are really the energy that the different points of the air are. So if you have air at 30 degree, 35 degree and 55 RH, and then you go down to there. I don't tell about what is the process, but let's say going from 1 to 2, then what you can see that you have these lines. So the enthalpy line is approximately, maybe if you look at the two, between 80 and 100, so it would be approximately 88 kilojoule per kg for this point. And then if you go to this point, you are down to something like 42 kilojoule per kg. So now if you want to calculate the enthalpy difference, you just look at these two lines. And this gives you how much is the difference. So it's about 46 kg per kg, 46 kilojoule per kg of dry air. And then if you want to calculate, that gives you an idea of energy per kg of air. It may not speak too much like that. I mean, it is the basic value, but at the same time, the physical value is there, but you would like to know more. For instance, what is the power of my cooling? So what you do is you simply, I have made it as simple as possible. So the thermal power of this process is the mass flow rate of air in kg per second multiplied by this difference of enthalpy. If you multiply this, it gives you kg per second times kilojoule per kg. That gives you kilojoule per second, so it's kilowatt. Kilowatt thermal, not electrical, thermal kilowatts. And then generally in the diagram you can say the difference, if it's positive, it's something like heating, more in the direction of heating. And if it's a negative value, it means it goes into cooling. Generally, I mean, it can be different, but... Okay, so I'll show you a kind of solution. So this is the sensible cooling. And then we have the transformation, that means cooling with dehumidification. So what is this kind of process? Tell me what it is. You know about it? In HVAC, the guy who knows HVAC or the woman who knows HVAC, it's quite, I mean, this is typically what you have. Let's say if you are coming directly with fresh air in a cooling coil, it's 40 outside, it's very humid, it's too much. I mean, even it's almost lethal climate what I have put here, but it was just to show. And here what you see is that you will go in the cooling coil, it will start by cooling without dehumidifying. Actually, it will do maybe the real process would be more like that. But to make it more easier to understand, it's like if you had, let's say, two cooling coils, one after the other. One which have water in the range of 20 degree, that would do this one, and then the one here has water in the range of 6 degree maybe. So you pass the air through one cooling coil and a second cooling coil to make it like that. And now what happens is that you have now the dehumidification, I mean, the cooling with dehumidification is taking you 47 kilojoule per kg as compared to 15 for the first. So now if you look at the ratio, and if you think of the enthalpy difference, right? So for 15-degree difference in the first phase, this is the enthalpy difference we get, right? And now this is what we have for the second 15-degree difference, but with the phase change, with the condensation of water in the cooling coil. And so it shows what? It shows that you are consuming, instead of, let's say, 30, if it was without removing water from the air, you consume something like 47, 50, something like 70 or something. No, this would be 30, and this is 60 plus. So that means it doubles what you would theoretically think if you just cool air without thinking of the condensation. And this is one of the major issue in climate change coming in India and China and Brazil and Africa, because at the moment, let's say, most of the HVAC for comfort in offices are doing this. And so even if you think of raising a little bit this temperature, instead of going from 20, you go down maybe to 15, or I'll show it here, maybe it's better. Yeah. Is it showing? No, it's, yeah. If you say, if we could have chilled water in the range, if you make, for instance, radiant cooling, suppose, and you only dehumidify the air with what Rajan was talking about, the treated fresh air dedicated outdoor air unit, you can imagine that instead of going down to this level, you could have water maybe at 16, 18 degrees for radiant panels. So you would already remove this only for the fresh air a little bit, you would use it. And that means you could significantly reduce the cooling load for the same cooling power, but simply not avoiding latent. So you see what you can see with this diagram. It's very powerful, because even if you are not knowledgeable in the detail of heat transfer and this, you can see the major principle. And if, for instance, an engineer tells you, I will cool the water at 6 or 5, then you say, no, pagal hai, it's not like this. You should do it differently. And with the season, you should also make it gliding. For instance, many people do cool too much all the year. So if you don't do that, you can save a lot of energy by trying to glide this temperature. So if you are... Yes, thank you. So this, I think, this was essentially to show you about this important understanding of sensible and latent. You will see, on the other hand, how you can use it in a positive way. So now, I show you the principle of the cooling on a more realistic climate. So here it is just typical things of Chennai. So if we take this point somewhere, and if we say now we are going to cool with a AHU with 100% fresh air, this is another thing which is also an issue. So if you cool with dehumidification, that means you will cool like you have seen now, down here, and then after, that means through the cooling coil, I have shown you this point 2 and 3. So the point 2 is, let's say, the beginning of the cooling, and the point 3 is after, let's say, at the end of the cooling. Then after, what does happen often, if you are in hospital or in some office, depending on the air distribution, you will have what is called reheating. That means you will not blow air 10 degrees on the head of people. Sometimes it's done also, but let's say generally people try to reheat a little bit. So you will need some heat. The heat for the reheating, you can get it indirectly from the cooling. Because if you have a chiller which is designed, and if the system is designed properly, you can use the heat that you remove here to put it back here. So this, we'll talk about it on Friday. And then you have also an additional heat, which are what is coming from inside the building. That means the gain from the external, from solar, from temperature, plus the internal gains. And so at the end, that's what you have. And then the return air is the 0.5, you can say. So this is if you do 100% fresh air cooling, which is silly. Normally you don't do that, but it's just to show the kind of energy you would need. So you go from here down to here. Huh? Now the interesting thing, which is another exercise that I would like to do with you. Yeah, okay. We should try to make mixing, because now if you want to recycle, let's say now we have said 100% fresh air. Now you say, okay, now I want to recycle some of the air. That means some of the return air from this return air, I would like to return part of it here and not cool all the fresh air, but having air which is already with less moisture, because the air here has much less moisture than this one, and it's also cooler. So if I can recycle part of it, I will save energy. And that's, I think essentially we have 15 minutes left, I was told, so it's not much. So maybe we drop this one, because this one, for the one who are really interested, we can work it later, I think, in the evening or whatever. Because if we want to finish, I would prefer show you the evap cooling also, because I think evap cooling has a huge potential in the hot and dry and composite climate. And I think this is, I show you then the results rather than, I think. So the trick in mixing stream is that, let's say now you are going to mix, you say I'm recycling 85% of the air from this point, and I try to go here. So then I will try. So actually, if I have 85% of recycling and 15% fresh air, I would say it's quite easy. You take the point of fresh air, you take the point of return air, and you take the kind of reverse distance between you are taking only 15 of fresh air and 85% of recycling. So actually from here to here you see that this point comes at 15% and 85% distance of these 2 points. So this is quite simple actually. Actually it's once you know how to do it. And that means you can have a straight line where you just calculate the 17%. So you can draw it actually. You take a scale, and you say, okay, now I take 85% between these two, and I put this point here. And then you get the airstream mixing. So this is how you get this point. I think it's quite easy, but you need once to apply, and you can find on YouTube or whatever, it's explained quite often. But so you get this point, and that's how you can then calculate. And then after that, now if you compare the two things, this is again silly to make 100% fresh air, but it's to show the impact of recycling with humid air, which is absolutely enormous. So now if we take let's say the 100% system, and with the recycling, you can see that we have, this one, that this is the cooling point where you start without recycling, and you go down here. Now with the recycling, you start from here. So you start on this, and so that means what you have, this is the total cooling with fresh air, and this is the total cooling with recycling. So it shows you the importance of recycling, and I don't go into heat recovery because it's with enthalpy, it's a little bit more complex to treat on the, let's say on the diagram. But I think these are some of the basic things that you can recognize and use and even discuss when you have to deal with project where you have to fight with HVAC engineer who want to put water at 5 degrees. You can explain them how and who would also like to put too much fresh air. You can see the combination of these two, how much it does. With the same thing, you can say the HVAC installation would be quite the same, doing the same thing. So now I think as a last exercise, we quickly try to do this. This is a point, let's say, typical of Ahmedabad climate in hot summer. And this is the kind of ISO. So now I would like you to try to calculate, to draw the evap cooling from 38 degree and 22% relative humidity. And you have the direct evaporative cooler is a relatively good one. It allows you to reach 80% humidity from the starting point. So you need to draw the evaporative cooling process. And then you can add also the 5 degree heat gain you have after the evaporative cooling process. That means once you are inside the building, there will be a heat up of about 5 degree. And then what is the energy requirement? That's what so I'll show you just the, let's say the solution. I have not, so the process follow the ISO enthalpy line. This is the main thing to remember. And then in terms of energy, what does it mean? Then some people have already answered, so what is it? What energy do you need for evap cooling? It's, you need what? No energy. In theory, you need no energy because you are just spraying water in air, and this is, so what you need physically is electricity, maybe to run a motor for a fan. You need to pass through the wet pad or through some other things. So you need some energy, but if you make the ratio between a good evap cooling with cooler, with a chiller, there is no comparison. So of course you don't have exactly the same humidity level, but when you have and even let's say with two-stage or indirect and two-stage cooling, you can sometimes reach temperature below the wet bulb that you will reach. So potentially in many of the hot and dry and composite climate, let's say evap cooling can be really a solution which is excellent for many situations, especially for residential and also even for office. Or it can be also in tandem in some cases, it depends how the things are in sequence, or it can be with the control. So I think that's, so I have just a quick 3-4 slides about the portable air coolers, because to me it's a kind of stupid use that many people do, and that's it's not only in India, that if you have let's say a portable air cooler, normally it's not ducted. That means it just takes the air that comes wherever from. If you have a cooler which is ducted, that means that you have a duct going through the envelope and that you are actually taking air fresh from outside. Then the air that you cool is nearing the wet bulb. That means the saturation curve that we were discussing. And the air will be then rejected. Now when you have this kind of cooler which are placed somewhere in the room, then what happens? There is a mixture. We just saw the recirculation before. It is involuntary, uncontrolled recirculation. So what happened is that some air is coming from outside, which is dry, hot, that you could cool. But a good part of the air, or maybe a lot, is coming back from the same air that went through the cooler. So it's like a chakra, it's just running. And so now if you compare the kind of potential you have, is that if you have 100% fresh air, that means recirculation rate is 0. With air at 38 degree, you can reach something like 25, 26 degree inside the ambient. Now if you recirculate uncontrollably, I mean without control, something like 80%, then your temperature is already at 32. And then it's then I have just drawn it the same, but with some drawing on the principle. But the main thing is to look at this curve. Is that what happened is that if you look at the recycling ratio. That means as you don't control, you don't know, and many people must be around here. So the blue gives you the temperature that you would get in the room, more or less. It's approximate, but it's quite, I think, relevant in terms. So if you have air at 38 degree that you're cooling at 25 degree, you can say even a little bit below, then if you are not getting ducted inlet or controlled inlet somehow, and you have something like 80% recirculation or even 90, then you will reach 35 degree in the same room using a cooler. So just think about it. It's a very practical kind of example. I think for people working, living in hot, dry and composite climate, this new tendency of the air cooler. And another thing that Rajan was saying is that very often the people, to show you how it's cooling nicely, you are in a big hall where the temperature and humidity is controlled, and they switch it on and show you how it is cool. Of course, you are taking the air from a big hole, so there is not yet the recirculation. You have, so it gives a completely false indication of the potential of the machine. So this is, so just as a quick conclusion, I would say it gives an entry for non-specialists in the understanding of how you are handling air with HVAC. I think it allows also a rapid air ventilation related processes analysis. Then it may also help in the dialogue between architects and engineers on ventilation and AC and beyond somehow, because we have talked about comfort, can be also discussing, we can say comfort, somehow design, somehow the kind of technical thing. So thank you.